Now in this lecture, the numerical part based on three-dimensional fluid flow, that is the continuity equation in three-dimensional fluid flow, and Cartesian coordinates as well as in polar coordinates we discussed in previous lecture. Therefore, the example is given here. Determine which of the velocity component. Here we see, determine which of the velocity component sets given below satisfy the equation of continuity. Three parts asking in that question. That is, the first one is the u is equal to a sin xy, v is equal to minus times a sin xy. In second part of the question, u is equal to x plus y and v is equal to x minus y. Third part of in this question, u is equal to 2x square plus 3y, v is equal to minus times 2xy plus 3y cube plus 3zy, and w is equal to minus times 3 by 2 z square minus 2xz minus 6y z. This is the complete question. Now we come on the first solution of the first part of the question is here. That is, the u is equal to how much? Given is a sin xy and v is equal to minus times a sin xy, which is see here. Therefore, differentiating the above both the velocity component with respect to the x and y, because u is the velocity component along the x-axis and v is the velocity component along the y-axis. Therefore, del u upon del x is equal to a y cos xy. Sin theta differentiation is how much? Sin theta cos theta. Okay, and sin theta is already cos theta with minus sign. That is the del v upon del y is equal to minus times a x cos xy. Therefore, applying the continuity equation, two-dimensional continuity equations, that is the del u upon del x plus del u upon del v upon del y is equal to 0, which is see here, and putting the value above we calculated, that is the del u upon del x and del v upon del y. In that equations we have ay cos xy minus ax cos xy, which is not equal to 0. That is, the continuity equation is not satisfied, and therefore this fluid flow is a not continuous flow. Okay. Now we come on second part of the question. Second part of the question, given velocity component at the direction of x is u is equal to x plus y, and velocity component along y axis is given as v is equal to x minus y. Now same differentiating both the above velocity component with respect to x and with respect to y, because the u is the velocity component along the x axis and v is the velocity component along the y axis. Therefore, del u upon del x is equal to how much? That is the 1, and del v upon del y is equal to minus 1. And now applying the continuity equation in two-dimensional flow, that is the del u upon del x plus del v upon del y is equal to 0, and putting these values, and we have 1 minus 1 is equal to 0. Therefore, we can say that this equation is continuous equation, because this value is satisfy the continuity equation. Now next one, come on the third part of this question, which is see here. In third part of the question, first velocity component and second velocity component and third velocity component. Three velocity component is given, that is the three-dimensional flow. u is equal to 2x square plus 3y, v is equal to minus 2xy plus 3y cube plus 3zy, and w is equal to minus times 3 upon 2z square minus 2xz minus 6yz. Now differentiating above the velocity component with respect to x, y and z, because the u is the velocity component along the x-axis and v is the velocity component along the y-axis and w is the velocity component along the z-axis. Therefore, differentiating above, del u upon del x, del v upon del y and del z or del w upon del z is equal to calculated. And applying the continuity equation in three-dimensional flow, that is the we all know del u upon del x plus del u v upon del y plus del w upon del z is equal to 0. Putting all these values, and which is not is equal to their 0, therefore we can easily say about this fluid flow is not continuous and this fluid flow is discontinuous flow. Okay, therefore now next example discussed here, that is the question. This example we understand about. Firstly, in this question, calculate the unknown velocity component in the following so that the equation of continuity is satisfied. First, u is equal to a e to the power x and v is equal to calculated. Second one, u is equal to a ln x upon l, v is equal to calculated. Third one, u is equal to calculated and v is given, that is the axy. Now solution of the first part, we come on, u is equal to given, that is the a e to power x, v is equal to not given, that is the calculated value, calculation part. Therefore differentiating this equation, del u upon del x is equal to a e to the power x, that is the a e to the power x, and which is equal to minus del v upon del y. Therefore v is equal to how much? Putting this value, this terminology we taken, this terminology is taken. Okay, integral of minus a to the power x multiplied by dy. Therefore solving these equations, and this is the minus a e to the power x into y plus fx, that is the answer. Second part of the question, u is equal to minus a ln x upon l, therefore v is equal to calculated, del u upon del x calculated, a upon x upon l into 1 upon l is equal to minus a upon x, because l will cut it out, which is equal to minus del v upon del y, and this relation is taken, minus cut it out, and we solve. V is equal to how much? Ay upon x plus fx, function of the x. This is the answer. Now third part of the question, which is C, third part of the question, u is equal to not given, v is equal to axy. Therefore differentiating the velocity component v is with respect to y, del v upon del y is equal to ax is equal to minus del u upon del x. Taking these above last two relations, last two relations, ax is equal to minus del u upon del x, and solving the above equations we get minus times here ax square upon 2 plus a function of the y. This is the answer of the given question. Now we come on another types of example. In this example, in three-dimensional incompressible fluid flow, that is the condition, given condition. In three-dimensional incompressible fluid flow, the velocity components in x and y directions are given here. U is equal to, right now here, x square plus y square z cube, and v is equal to minus times within bracket xy plus yz plus zx. Use continuity equation to evaluate an expression for the velocity component in component w in the direction of z axis. Okay, which is question asking in question about we calculate the velocity component about z axis. Okay, this example is asking in Bangalore University. Therefore, now come on the solution of that questions. The continuity equation for steady three-dimensional incompressible fluid flow is del u upon del x plus del v upon del y plus del w upon del z is equal to 0. Therefore, firstly, the two velocity component is given and both velocity components is differentiating with respect to x and y. That is the del u upon del x is equal to 2x, y component is already, yz is component is 0, and del v upon del y is how much? That is the minus times x plus z. Putting these values in equation, which equation? The continuity equation. Therefore, we get this equation, and solving these equations we have del w upon del z is equal to minus times x plus z. Integrating with respect to the z, we have the velocity component along the z axis is how much? Minus xz plus z square upon 2 plus c, where c is the function of x and y. Therefore, the velocity component of the z axis is calculated. W is equal to how much? Minus x plus z square upon 2 plus f, the function of x, y. That is function of x into y. Now, the next example is taken. The next example is given the velocity component u is equal to logarithm base e is y square plus z square, and w is equal to logarithm base e x square plus y square. Okay. Therefore, what is the most general form of v so that the flow is possible for a steady three-dimensional incompressible flow or not? Possible or not? Therefore, we come solution part. We come on the solution part here. That is the u is equal to and w is equal to is given. Therefore, now differentiating both the velocity component with respect to x and with respect to z, because the x-axis component is given and z-axis component is velocity component is given. Therefore, del u upon del x is equal to 0, del w upon del z is equal to 0. Putting these values in the continuity, three-dimensional continuity equations, which is see here, del u upon del x plus del v upon del y plus del w upon del z is equal to 0. Therefore, del v is equal to del v upon del y is equal to 0, and integrating both the equation, del v is equal to the function of x into z. By symmetry, one of the values of velocity component could be v is equal to logarithm base e is equal to e multiplied by x square plus z square, which is the answer, which is see here. Okay. Now we come on next example. We see here, for an incompressible fluid, the velocity component are u is equal to x cube minus y cube minus z square x, v is equal to y cube minus z cube, and w is equal to minus 3x square z minus 3y square z plus z cube upon 3. Therefore, determine whether the continuity equation is satisfied or not. Similar work of that question, we have, that is the all velocity component which is C here, and differentiating the all velocity component with respect to the x, y and z, we get del u upon del x is equal to 3x square minus z square, del v upon del y is equal to 3y square, del w upon del z is equal to minus times 3x square minus 3y square plus z square. Applying the continuity, three-dimensional continuity flow of the continuity equation is del u upon del y del x plus del v upon del y plus del w upon del z, putting the all values and gives out 0. Therefore now we can say that the velocity component, all velocity component is continue, that is the continuity equation is satisfied. Now we come on next type of example. This example we see here, the velocity component in x and y directions are given as u is equal to 2xy cube upon 3 minus x square y, and v is equal to how much, xy square minus 2yx cube upon 3. Indicate whether the given velocity distribution is, first part and second part, two parts is asking. First one is a possible field of flow and second one not a possible field of flow. Okay, therefore given velocity component u and v are here, we see in the question here, a possible flow field in two-dimensional must satisfy the continuity equation is here, del u upon del x plus del v upon del y is equal to 0. Therefore now calculating the velocity component with respect to the x and y, del u upon del x and del v upon del y is here, both are calculated. 2 upon 3y cube minus 2xy and dv upon dy del v upon del y is equal to 2xy minus 2 by 3x cube. Putting the all values in the continuity equations, two-dimensional continuity equations. Therefore the continuity equation is not satisfied, the given velocity component, therefore do not represent a possible flow field. Okay, yani ki first part here, which is the first part of the question is satisfied, second part of the question is not satisfied because not a possible flow of the field of the flow. Okay, another type of example we see here, that is the in an incompressible flow, the velocity vector is given by v is equal to 6xt plus yz square I plus 3t plus xy square j plus xy minus 2xyz minus 6tz into k. Verify whether the continuity equation is satisfied, first part, and second part determine the acceleration vector at point L is given 2 at time t is equal to 2. Now come on the solution part of that question, which is here. Okay, here the velocity component capital V is equal to given. Now equating the standard equations, that is the ui plus vj plus wk, therefore u is equal to 6xt plus yz square, v is equal to 3t plus xy square, w is equal to xy minus 2xyz minus 6tz. Now differentiating the all velocity component velocity component u, v, w with respect to x, y and z, we have del u upon del x is equal to 6t del u v upon del y is equal to 2xy, and del w upon del z is equal to 2 minus times 2xy minus 6t. Therefore, the continuity equations in three-dimensional flow is how much? That is the del u upon del x plus del v upon del y plus del w upon del z is equal to, putting the all values, and which is given as, which is calculated as, which is find out 0. Therefore, we say that the continuity equation is satisfied. Now we come on the second part of the question, that is the acceleration. Acceleration A is equal to a suffix xi plus a suffix yj plus a suffix zk, which is C here. That is the acceleration. We know that ax is equal to del u upon del t plus del u upon del x plus v del u upon del y plus w del u upon del z, which is the acceleration component ax. Putting the all values in the above equations, therefore at the time t is equal to 2 seconds and 0.222 x y z is 22, which is taken, which is given in question. Putting all the value in the equations ax and calculate all these terms, we get 164 unit, which is the acceleration component along the x-axis. Okay. Now similarly, along the y-axis, del v upon del t plus u del v upon del x plus v del v upon del y plus w del v upon del z, which is C here, that is the ay. And putting all these values and taken a point a222 at time t, which is solving the above, and we get 243 units. Similarly, z already calculated, and which is solved, that is the calculated value is 432 units. Okay. Now therefore come on the final result. A is equal to axi component plus ayj component plus azk component, putting all these values. Therefore the acceleration A is equal to how much? 164I plus 243J plus 432K, which is answer. Okay. Now last question is about a two-dimensional. Last question we come on the based on the polar coordinates of the fluids. Continuity equations according to about the polar coordinates. A two-dimensional incompressible flow in cylindrical polar coordinates is given by Vr is equal to 2r sin theta cos theta, and V theta is equal to given as how much? 2 minus times 2r sin square theta, which is C here in the question. Okay. Determine whether these velocity components represents a physically possible flow field. Now we come on the solution part. The continuity equation, we know about the continuity equation in polar coordinates of two-dimensional incompressible flow is Vr upon r plus del Vr upon del r plus del V theta upon r del theta is equal to 0. Therefore, from the given velocity component, del Vr upon del r is equal to del upon del r 2r sin theta cos theta is equal to 2 sin theta cos theta, and del V theta upon del theta is equal to how much? Del upon del theta minus 2r sin square theta is equal to minus times 4r sin theta cos theta. In these values in the above equations, putting the above equation in continuity equations, and here therefore left hand side is equal to 0. Okay. 2 sin theta cos theta plus 2 sin theta cos theta is equal to 4 sin theta cos theta and cut it out. Therefore right hand side is equal to left hand side, which is equal to 0. Therefore thus the continuity equation is satisfied, and hence the flow is physically possible, and the fluid flow is continuous flow. Okay, now we come on the last example. Another type of example, these the tangential component of the velocity in a two-dimensional flow of incompressible fluid is v theta is equal to minus times c sin theta upon r square, where c is a constant value. First one, using continuity equation, determine the expression for radial velocity, that is the v, and second one is find the magnitude and direction of resultant velocity. Solution of that part: the given velocity, radial velocity, is tangential velocity component is minus c sin theta upon we see here is minus c sin theta upon r square. Therefore expressions for v are according to the continuity equation polar coordinates. We write here, that is the Vr upon r plus del Vr upon del r plus del v theta upon r del theta is equal to 0. Therefore putting all these above values, we have the velocity component is solving about the velocity component minus c upon r square cos theta. From both equations, putting all these values and equating both sides and integrating both sides of the equations, which is c here, and therefore radial component of the velocity Vr is equal to minus times c cos theta upon r square. Resultant velocity is how much, which is calculated, that is the resultant velocity component under root v square Vr square plus v theta square. Putting the both velocity component, radial and tangential velocities, and squaring both and solving about cos square plus theta plus sin square theta, which is equal to 1, and final the result is resultant velocity is c upon r square. Okay, now after completing the continuity equations in Cartesian coordinates and polar coordinates, we and different types of numerical discuss in that previous lectures and within that lectures. Now come on, the next topic is circulation and vorticity. Okay, circulation and vorticities, two terms we see here, that is the circulation and vorticity. Now let us consider a closed curve in a two-dimensional flow field, which is seen in the diagram. The curve being cut by the streamlines, let P, that is the streamline point P, be the point of intersections of the curve we see in the diagram, and the curve with one streamline, theta be the angle with which the streamline makes with the curve, which is theta angle, and the component of the velocity along the closed curve at the point of the intersection is equal to be the capital velocity component is v cos theta, which is the velocity component, and which value is how much, that is the v cos theta. Circulation is denoted by, here we see in diagram, this is the chi or tie we see here, this is the denotation of the circulation. And tangential velocity about a closed path contour, which is the we know about the definition of the contour studying in mathematics. Chi is equal to integral of closed curve contour, closed curve integral of v cos theta into ds, where ds is the element, particular length of the element. V is equal to how much? V is the velocity in flow field at the element ds, that is the taken as element ds. And theta is equal to how much? This is the angle between capital V and a tangent to the path at that point. That is the in positive and anti-clockwise direction along the path, which is positive taken as anti-clockwise, which is taken as positive. Now, circulation along regular curves can be obtained by intersection. Let us consider the circulation around an elementary box, that is the ABCD, which is shown below. ABCD, that is the fluid element ABCD, which is seen in the diagram. Starting from a point, proceeding anti-clockwise, we have d chi is equal to how much? U delta x plus v del v upon del x delta x into del y, and minus times u del u upon del y delta y into dx minus times u delta y. And solving the above equations, we get del v upon del x minus del u upon del y delta x into delta y. Now therefore the vorticity is defined as the circulation per unit of enclosed area, that is the vorticity. Vorticity is defined as, which is denoted by ohm, and it is defined as the circulation per unit enclosed area, that is the chi upon A. Therefore ohms, that is the vorticity, is equal to d chi upon del x into del y, and that value is equal to del v upon del x minus del u upon del y from the above equations we taken from here. And now we can write, if flow possesses vorticity, it is rotational. That is, the rotation is denoted by omega, and it is defined as 1/2 of the vorticity. Vorticity rotation is how much? This is the half part of the vorticity, and omega is equal to 1/2 del v upon del x minus del u upon del y, which is C here. The flow is irrotational if rotation omega is 0. Okay, therefore here the flow is 0, irrotational, therefore rotation omega is 0. Therefore, if possible about for 3-dimensional flow, the rotation is possible about 3 axes x, y and z. That is, the rotation is expressed in terms of omega, that is the w, omega x, omega y and omega z can be obtained in like that. Omega z is equal to how much, which is 1/2 del v upon del x minus del u upon del y, and omega x is equal to how much, that is the 1/2 del omega upon del y minus del v upon del z, and del omega y is equal to, and that is the rotation about y axis, and the plane is xz, that is the 1/2 del u upon del z minus del w upon del x, which is all are the velocity rotation components along x, y and z. In the vector rotation, the equation can be written as omega is equal to 1 by 2 multiplication whole within bracket wxi plus wyj plus w2z wzk, which is see here, and we written this terms is written as the 1 by 2 delta into v. The vector delta into v is the curl of velocity vector, that is the curl of the velocity vector. Therefore, vorticity in a fluid motion is taken numerically equal to twice the value of rotation. Therefore, vorticity is written here omega, that is the ohm, that is the vorticity is equal to curl of v, that is delta into v. Therefore, which may expressed in the mod form, curl of v is I j k and del upon del x del y del z del upon del y del upon del z and u v w, which is written as vorticity xi plus vorticity in yj plus vorticity in zk, and the vorticity is expressed in similarly separately, which is see here, which is separately written as omega x, that is the ohm x, that is the vorticity about x axis is equal to 2 omega x, 2 times of the rotation. Okay, that is the del u del w upon del y minus del v upon del z and del y, and vorticity y is along y is equal to 2 omega y del u upon del z minus del w upon del x, and vorticity along z axis, that is the 2 omega z, that is del v minus del x minus del u upon del y. The motion is described as irrotational, which when the components of rotation are vorticity are 0. Understand? The motion is described as irrotational or irrotational when the components of rotation or vorticity are 0 throughout certain portion of the fluid. When torque is applied to the fluid particle, it will gives rise to rotation. The torque is due to shear stress, therefore the rotation of fluid particle will always be associated with shear stress, as the shear stresses in turn depend upon the viscosity. The rotation flow occurs where the viscosity effects are predominant. However, in the cases where the viscosity effects are small, the flow is sometimes assumed to be irrotational. This simplifies analysis of the problem of fluid flows. This is the completion of vorticity and circulation, both two terminology, that is the circulation and vorticity. That is the we conclude the complete topic, that is the circulation, and circulation is denoted by chi, that is the circulation is how much circulation is calculated, and it depends on the rotation, and rotation in the term of vorticity is 1 by 2 of the del v upon del x minus del u upon del y, that is the rotation along x axis, y axis and z axis. X axis is 1 by 2 del omega del w upon del y minus del v upon del z, and y axis 1 by 2 del u upon del z minus del w upon del x. That is the concludes in the vorticity and circulation. In the circulation, the rotation is about 1 by 2, half of the 3-dimensional fluid flow. And in the case of vorticity, the circulation, that is the 2 times of the rotation, that is the omega, that is the x is equal to 2 times of omega x. Okay, therefore the motion is described as irrotational when the component of rotation or vorticity are 0. Okay, now therefore the the topic is complete, that is the circulation and vorticity. Now we discuss the numerical part in the next lecture. Okay.